Hi, my name is Johnny Hancock from Agilent Technologies. I'm an engineer at Agilent's Design Validation Division located in Colorado Springs, Colorado. In this short video, we're going to show some comparison measurements of using serial bus triggering and decode. Today's embedded designs that you might be working on include a variety of serial buses such as I2C, SPI, CAN, and LIN. And being able to trigger and decode on these various protocols is very important as opposed to just counting bits like you've had to do in the past. In this demonstration today, we're going to show demos of CAN triggering and decode. Although you may not specifically be using CAN, maybe you're using I2C and SPI, some of the concepts we're going to talk about today apply to all of the various protocols. For this demonstration, we will show side-by-side measurement comparisons using two 1 GHz bandwidth oscilloscopes that have CAN bus options, the Agilent MSO6104A and the Tektronix DPO4104. For our CAN signal source, we are using a microchip CAN evaluation board. Let's begin by viewing a single CAN frame on the Agilent scope. The scope has been set up to trigger on a specific data frame with an identifier of 07F hex. Near the bottom of the screen, we can see data frame 7F captured on channel 1 of the scope. This is the yellow trace. At the very bottom of the screen, we see the color-coded hex level decode of this particular frame. We can see the first digits, 07F, identifies what it's decoding this frame to be. DLC equal 1 says it's got a data link code. There's 1 data byte to follow, and in this case it's 3. And then the last set of digits is the CRC. The blue traces near the top of the screen are signals captured on the mixed signal scope's logic channels. They're actually SPI signals from something else in the system. And the green trace, which is channel 2, shows the analog output level of what might simulate a remote sensor. This particular signal is converted to a digital value and then transmitted within this particular data frame as a data byte. At this time, the CAN frame is transmitting a data value of 3, as we can see in the decode. As we vary the sensor's output level with the scope's very fast waveform update rate, we not only see real-time updates of the CAN waveform, while captured with the MegaZoom deep memory, we can also see real-time updates of the decode string at the bottom of the screen. This is one of the key advantages of hardware-accelerated decode. We can observe dynamic signal activity and decode activity in real time. We have now injected an infrequent glitch into our CAN signal to simulate a signal integrity problem to see how the Agilent scope responds to errors. While observing the decode string at the bottom of the screen, we can see an indication of an occasional error condition color-coded in red. Without hardware-based decoding, we would probably not be aware of these error conditions because they happen so infrequently. Let's now set up the scope to trigger on CAN error conditions. By triggering on all errors, the scope now only captures and displays frames that either have a form error condition, such as a glitch, or triggers when the scope detects an active flagged error frame. Let's now stop acquisitions on one of these error conditions and perhaps visually analyze our CAN signal to see what is possibly causing this error condition. By panning and zooming on this stored waveform that we have just captured, now we can zoom in here. Now we see what's causing the problem. We have captured a glitch. This is a good indication that we may have a signal integrity problem in our design. Let's now set up the same measurements on the Tektronix DPO4000 series scope with its CAN option. Here we show the same CAN frame on the Tek scope while triggering on data frame ID 07F. Although this scope's default acquisition memory is just 10K points, we have selected to acquire 1 megapoint since deep memory is usually required when capturing serial packets to avoid undersampling, especially when dealing with high-speed CAN applications such as 1 megabit per second. At this memory selection, the waveform appears to be updating fairly fast when we change the sensor's output value, but the decoding rate lags behind with an approximate update rate of 1 decode every 1.5 seconds. This is because this scope utilizes post-process software decoding as opposed to hardware-accelerated decoding like on the Agilent scope. This means that waveforms and decode strings are not directly correlated when viewing dynamic activity like we have here. Let's now try the scope's deepest memory selection, which is 10 megapoints. Unfortunately, when using 10 megapoints of memory, waveform and decode update rates slow to approximately 1 update every 15 seconds due to the post-process technique of decode in this scope. Acquiring and decoding with 10 megapoints of acquisition memory may be okay for single-shot applications, but it is not a good selection for observing dynamic activity and when looking for infrequent problems. So let's now turn down the memory selection back to 1 megapoints to make it a little more usable, and then inject our occasional glitch, like we did with the Agilent scope, into this bit stream to see how the TEC scope responds to error conditions. With the decode update rate every second and a half with 1 megabyte of memory, this scope is unlikely to detect an error condition due to this glitch that we've inserted while triggering on this particular frame, 07F. Just like fast waveform update rates are important to capture random and infrequent signal anomalies, fast decode update rates are also important to detect infrequent error conditions in serial bus communication. Let's now go back to CAN measurements on the Agilent MSO 6000 series scope to show another benefit of hardware-accelerated real-time decode. We have now set up our CAN demo system to generate flagged error frames. While again triggering on data frame 07F with the fast waveform and decode update rates, we see the occasional occurrence of these error frames. Now that we know that flagged error frames are occurring, we can set up the scope to trigger on these particular error frames. And as you can see, we're triggering on quite a few error frames. In addition, with hardware-accelerated triggering and decoding, the MSO 6000 series scope also displays a totalized count of various frame types, including total frames, error frames, as well as bus utilization, or what is sometimes called bus load. This totalize function is not based on acquisition time. Frame counts are totalized even during the scope's dead time, meaning that we have a real-time count of all bus efficiency data. Here we can see that approximately 12% of our CAN bus activity consists of error frames. This indicates a pretty severe problem in our simulated CAN design. Let's now view the same CAN conditions on the TEC DPO 4000 scope. On the TEC scope, we are again triggering on data frame 07F. But because of the slow waveform and decode update rates, we are not observing any error frames. But we know that they are occurring at an approximately 12% rate as measured on the Agilent scope. Unfortunately, the TEC scope does not have a totalized function to verify this. However, let's try triggering on just error frames like we did on the Agilent scope. Even with error frame triggering selected, this scope doesn't appear to be triggering on this condition, even though we know this condition is occurring. But if we select a trigger on overload frames, now the scope appears to be triggering on error frames and decoding error conditions. We believe this must be a firmware bug in the oscilloscope, which was updated in May of 2006. Perhaps this apparent problem will be fixed in the future. Besides fast waveform update rates and fast decode update rates, as well as the bus efficiency totalized functions that are available in the Agilent MSO 6000 series scope, another big advantage of hardware accelerated decode is that the CAN triggering as well as the CAN decode is based on the same exact hardware. That means you get direct correlation between triggering and decoding. However, on the Tektronix DPO 4000, triggering is based on hardware, but decoding is based on software. And as we just saw in this side-by-side demonstration, measurement results of triggering and decoding don't always correlate. So, if you want a tool that can help you debug your embedded designs faster, that may include serial bus protocols such as I2C, SPI, CAN, or LIN, consider the hardware-accelerated triggering and decode advantage available in Agilent's MSO 6000 series oscilloscopes. Thank you.